Okay, so since lectures were kind of long on these sections, I decided to do these in-class problems separately. But I'll do all the odd ones here, and then we'll still do the even ones in class. So the first part was just to be able to convert our pressure readings. So for the first one, we're converting everything to PSI. So you will be provided with this, but you're gonna have to go look it up. You're gonna have to know one, you're gonna have to go look it up. You don't have to know it, you have to go look it up. So you have to know where to find it. 14.7 PSI, which is also equal to 760 millimeters of mercury, which is also equal to 101,325 pascals, okay? So we're converting all of these readings to PSI. So the first one, 0.988 ATM. So we always want to put what we're starting with on the bottom. We want to put what we're going to, PSI. So you have to remember that that was the 14.7 PSI in 1 ATM. So 0.998 times 14.7, 14.5 PSI. Don't forget your units. Be very careful about your units. B, 748 millimeters mercury. Okay, so we know we want millimeters mercury in the bottom. So that's 760 millimeters mercury. And then on the top, we want to go to, what are we going to? PSI. We know that that's 14.7 PSI. Okay, so 748 times 14.7 divided by 760. Well, look at that. Guess what? 14.5 PSI. I think it's funny your book did that. All right. C, 1,100, 101,000. Why do I keep getting that wrong? 278 pascals. So we know we have 1,100 and 325. 1,000. I did it again. I did it again. Why? I'm just not going to say it anymore because I'm just going to get it wrong. 14.7 PSI, and that gives me 14. That's not right. I did the math wrong on that. I did it in the calculator again, 101. Oop, 101, 278 divided by 11325 times 14.7. Do that, 278, 325, yeah. It rounds to 14.7, okay. PSI, okay. All right, let's see. Skipping that one. All right, now, suppose you had the same amount of gas in two identical containers, container A and container B. Container A is at 300 Kelvin and container B is at 350 Kelvin. Which gas is at higher pressure? So what you have to remember, right? Remember I told you there were two things. There are two things that you'd remember. PV is equal to nRT, PIV nert, and you had to remember your peas and vegetables on the table, right? Peas and vegetables on the table equal to a constant. So if you increase your temperature, we're going to do this logically, and then we're going to look at our formulas. So if we increase the temperature, that means our particles are going to move faster. So gases move faster. When the gases move faster, that means they have higher kinetic energy. That's the definition, right? So if they have more kinetic energy, the particles will hit the sides of the container. More, right? At higher temperature, they're going to hit the sides of the container more. What is that? That is the definition of pressure. Okay. Well, you could use your peas and vegetables on the table too. It's so what happens, or your PIV nert, right? Let's do PIV nert. So we're saying we're going to increase temperature. So if you increase temperature, what's going to happen? Whoa, If you increase temperature, what's going to happen to pressure? I want to keep this side of the equation equal to this side of the equation. So if I increase something on one side, I have to increase something on the other side. What am I going to increase? Pressure. Okay? You can do it any which way, but just know that there's more than one way to think about a lot of these problems. Okay, so we're going to go down to 7.5. A child's balloon containing 8.5 liters of helium gas is at sea level, is released and floats away. What will the volume of helium be when the balloon rises to the point where the atmospheric pressure is 380 millimeters of mercury? I see something there that's an initial condition and a final condition, okay? So let's write down what we know from our question here, right? What were we told about the volume? So initial, go back and look. Initial is telling me my volume was 8.5 liters. It's also telling me that it was at sea level. What is sea level? Sea level is the same thing as 1 ATM. You have to know that. You have to know that. What is the same thing as 1 ATM? 760 millimeters of mercury. Okay, so they want the answer. You could give it in either one so long as you have the initial and the final in the same unit. So what were we given in final? We were given a volume and we were given a pressure. Final. Our volume that we were given, oh, that's our unknown. We weren't given it. That was the unknown. What is the volume? What pressure were we given? The atmospheric pressure is 380 millimeters mercury. So when I use this, I want to use this one and this one in my formula because they have the same units. If they don't have the same units, units won't cancel out and our answer won't be right. So you have to be careful about that. So remember your peas and vegetables on the table. Start with initial, go to final. Okay, so are we worried about temperature? Nope. So we can kind of cross it out and just look at pressure and volume. So if we have 760 millimeters mercury, our initial volume was 8.5 liters, and our pressure final was 380 millimeters mercury, and our volume final is our unknown. So divide by 380, divide by 380. Make sure your units cancel, right? So what are we left with? 760 times 8.5 divided by 380. You should get something that is 17 liters for your final volume. Okay, so now does that make sense? Well, yeah, if we look at PivNert, right? What happened in our condition? What did we change? Well, we changed our pressure. Our pressure went from 760 to 380. So if our pressure drops, what happens to, what are we looking at, volume? Well, if I want this side of the equation to equal to this side of the equation, what does that mean? That means that my volume has to go up. Well, we went from a volume of 8.5 liters to a volume of 17 liters. Check, we're good. We are good. Okay, 7.7. A balloon is blown up to a volume of 0.5 liters at 72 degrees Fahrenheit. I can't believe the book gave you this one. It's Fahrenheit. It's the big F. Y'all know that's the F word to me, right? I'm not going to give you anything in Fahrenheit. Yes, you have the formula to convert, but I'm not testing you on that on this exam. So remember, if you're given something in Fahrenheit, this is a pain in the butt. You have to convert to Kelvin, then you have to convert to, you have to convert to Celsius and then to Kelvin, right? So you have to go back and look on your formula sheet, and your formula sheet is degrees Celsius, degrees Fahrenheit, minus 32 Fahrenheit, plus 1 degree Celsius over 1.8 degrees Fahrenheit, right? So to get your degrees Celsius, you go 72 minus 32 plus, so that's kind of all together that you have to do, plus 1 over 1.8. And so you get your degrees Celsius is like 22.2 degrees Celsius. How do you get from Celsius to Kelvin? This is the one you have to be able to do. You have to be able to go from Celsius to Kelvin. To go from Celsius to Kelvin, you add 273. So now we get 295 Kelvin. You have to be able to do this one. I'm not going to expect you on the exam to go from Fahrenheit to Celsius, but I will expect you to go from Celsius to Kelvin. But that conversion is in your sheet, so don't fret too much about that. Okay, so let's talk about our conditions. We know we had initial and we have final. Okay, so initially our balloon is blown up to a volume of 0.5 liters. And we had a temperature, we did all that conversion, and we got 295 Kelvin. The balloon sits in a car that reaches 103 degrees Fahrenheit. Assuming constant pressure, what is the new volume? Volume final, we don't know. And I am going to tell you, I'm going to do the conversion for you. That is 103 degrees Fahrenheit. I'm telling you that that is 312 Kelvin. Because I'm not going to make you do that. I'm not. All right, so what are we doing? We're doing our peas and our vegetable on the table. Peas and vegetables on the table. Initial, final. Now, what are we holding constant? Assuming constant pressure so we can get rid of pressure. So now our initial volume was 0.5 liters. Our initial temperature was 295. Our final volume is unknown, and our final temperature is 312 Kelvin. So you just gotta cross multiply, 312, right? 312, okay, so those cancel. So 312 times 0.5 divided by 295. What do you get? You should get a final volume of 0.53 liters. Now, does this make sense? Remember your PivNert. What are we doing here? We had our temperature, we knew, went from 395 to 312. So that means we increased our temperature. If I want this side of the equation to equal this side of the equation, I need to increase something on this side. So what's going to increase? That's my volume. So did my volume increase? I went from 0.5 to 0.53. Yes, I did. Okay, just a good double check. You always want to make sure that you're doing the right thing. All right, 7.9. Nitrous oxide, NO2, or laughing gas, is a common anesthetic agent. A cylinder containing nitrous oxide is emptied. What happens to the pressure in the tank? Okay, PivNert. I'm telling you, PV equal to nRT. All right, what we haven't talked a whole lot about is our number of moles. So N right here is our number of moles, right? That's number of particles. So what happens? Well, if I decrease the number of moles, so I make something on this side of the equation get small, what do I have to do over here? I'm going to have to change it. So what's going to happen to the pressure? It's a tank. You can't change the volume. So if you can't change the volume, you have to change the pressure. It's going to decrease. So your pressure will decrease. You have less gas in the same volume. And so you're going to end up with, and same temperature, and same temperature. And so you're going to have less collisions, right? And that's going to equal to a decrease in pressure, okay? And you can answer all of this with PivNert. PivNert's so cool. You can answer so much with it. All right, a balloon is filled with helium gas, which is lighter than air. Which of the diagrams, A, B, or C, looks most like the new volume of the balloon when the following changes are made? So I'm going to suggest you write PivNert. And I kind of want to look at this, and before I read my questions, if I select A, what's happening? I am going to decrease my volume, right? Because I went from here to here. Well, that was a decrease in volume. How about B? when I go from here to here. This is no change in volume. And how about C? C, our volume goes up. So an increase in volume. So just so I know what's going to happen before, what my answers are really saying before I go read my question. So a balloon floats to a higher altitude where the outside pressure is lower, but the temperature is the same. Well, look at your Pivnert. If I drop pressure down and my temperature is the same, then all of this is going to be constant. So how do I make this side equal? Well, what am I going to do? I'm going to do the opposite. I'm going to increase volume. So this must be an increase in volume. Which one's an increase in volume? That's answer choice C. Okay. The balloon is placed in a hyperbaric chamber where the pressure is increased, but the temperature stays the same. Okay, so let's do this. Our pressure is increased. We have an increase in pressure, but the temperature stays the same. So this again is constant. So what's going to happen to the volume? Well, if our pressure goes up, then our volume has to go down. So pressure went up. In this case, volume is going to go down. So in which one of these was my volume going down? And that's choice A. Okay. The temperature of the balloon. So here in C, our temperature increases. So what's going to happen when our temperature increases? Well, let me kind of erase this. If my temperature increases, what's going to happen if I have constant pressure? So this is constant and this is constant. So if my temperature goes up, I need to make the two sides equal. My volume is going to go up. So I need to increase my volume. So this would be choice C. D, the balloon is warmed and then cooled to its initial temperature and the pressure remains the same. If you started at an initial and your initial gets changed to some number, then we go back to our initial, all of our initial conditions are true. So there's going to be no change in volume. So that's our choice B. Okay. All right, let's see. All right. A 25 milliliter bubble is released from a diver's tank at a pressure of 4 atm and a temperature of 11 degrees Celsius. What is the volume of the bubble when it reaches the ocean surface where the pressure is 1 atm and the temperature is 18 degrees Celsius? Okay, let's jot down the information, right? The important thing is to keep your initial numbers together and your final numbers together. So initial, we had an initial volume, we have an initial pressure, and we have an initial temperature. Go back in and pull that information out. 25 milliliters for volume, 4 atm, and we have 11 degrees Celsius. Remember, this is one where you have to convert, but I'm expecting you to be able to do this. It's adding 273. So you get 284 Kelvin, okay? That's our initial conditions. Here's our final conditions. We don't know our final volume. We know our final pressure was 1 atm, and we know that our temperature was 18 degrees Celsius. Got to convert that. 273 gives us 291 Kelvin. Okay, now, peas and vegetables on the table. Final. Okay, are any of them held constant? Nope, they're all changing. So you can't get rid of anything. But isn't this nice where you don't have to remember whose law and what's the relationship? Put your peas and vegetables on the table and don't worry about it, okay? All right, so my initial was 4 atm. My initial volume, 25. My initial temperature, 284 Kelvin, okay, is equal to pressure final. I moved over too far. 1 ATM, I'm just too far over. And then my final volume was my unknown, and then I had 291 Kelvin, okay? So what I need to do is to cross multiply, so I'm gonna end up with 291 over here, right? And that's just one, so we don't have to worry about it. So my final volume is, if you put this all into the calculator, I got 102 milliliters, okay? All right, I think, is that, no, oh, I thought that was it. Not quite, not quite. This is the last one. All right, suppose you have two identical containers at the same temperature. One contains 4 moles of H2, the other contains 4 moles of O2. According to the ideal gas law, which one has the higher pressure? So remember, PV and RT, that's our ideal gas law. What's being held constant? Same temperature, so let's write our constants. Temperature. One contains 4 moles of O2, one contains 4 moles of O2. I'm sorry, H2 and O2. So our moles are the same, right? That's 4 moles. It's constant. According to the ideal gas law, which one has a higher pressure? Well, you have two identical containers. If they're identical containers, volume is also constant, right? So if temperature doesn't change, number of moles doesn't change, volume doesn't change, and R is already a constant, all of this has to stay the same. Can you have a different pressure? Nope. So all of them are constants. So which one has the highest pressure? They are at the same pressure. Kind of a trick question, but at least it wasn't a trick question on the exam, right? All right, y'all have a great rest of your day.